Does this work? No, okay. Yeah, why not? Okay, so my name is Alonso Silva. I'm a researcher at Nokia and also a researcher at Links. And this is a joint work with several people, Wentao, Joao, Dominique, several colleagues from Nokia, Hank, which is here, Ryan. So some of them are last year interns and PhD student and interns this year. Okay, the outline of the talk is the following. So this is a work related to structure. Structure thinking matters. This is the name of the paper. And it's related to structured outputs and structure generation. And then I'm going to present some current works, which are the follow-up of this work, and then the conclusions. So the first thing I want to start with is correlation is not causation, which I think that many people here already know. But the idea is if we look, for example, at the Google searches, so Google searches of spurious correlation, and this correlates very well with the number of consultants in West Virginia. And if you look at the p-value, is smaller than 0.001, which means that Fisher will say that this is there is some causation. So we reject the null hypothesis, and there is some causation. But in reality, if you search more for spurious correlation, you will not increase the number of consultants in West Virginia. And similarly, if you increase the number of consultants there, it will not increase the number of Google searches. So, and this work is about formal causal inference. So empirical or common sense causality is related to, for example, okay, smoking causes cancer, or let's say Alice slipped, so she fell down, which is, okay, I am going to make some common sense causality. In this particular case, is about formal causality, which means the kind of claims are related to the bottom one here. For example, suppose we know that A correlates with B, can we infer that A causes B? Or A correlates with C, B correlates with C, however, A is independent of B, can we infer that A and B have a common effect? So this is going to be the kind of question that we're going to deal with. And this is coming from a paper. So the inspiration of this work is coming from this paper, which appeared in ICLR 2024, which asks the question, can large language models infer causation from correlation? And the paper, well, this is the link to the archive paper. But what is interesting about this paper is that it produced one data set, which is core-to-cause. And the kind of question that core-to-cause has is the following. So for example, this is an example of a question. Suppose there is a closed system of 3 variables, A, B, and C. All the statistical relations among these 3 variables are as follows. All of them are correlated, and A and C are independent given B. And as you can see in the right-hand side of the slide, there are several different causal Markov equivalent classes. So basically, which caused what other thing. So in this particular case, A caused B and then B caused C. So there are all these different hypotheses. And so these are all the possibilities that there exist. And then you ask the model, okay, does this imply that A directly causes B? And the possible answers the model can give is yes or no. And if the language model just come up with an hypothesis, which for example is the first one, A causes B and B causes C, then he will say yes. And but this will be incorrect because you need to basically falsify all the other hypotheses to say, okay, that means that necessarily A implies A causes B. And the metric that they use in the paper, it is precision, recall, and F1, just as to recall. So basically precision is, and why do they use this instead of accuracy? Because the data set is very unbalanced towards false. So they have, so precision is how many retrieved items are relevant, and recall relates to how many relevant items are retrieved, and F1 is just the harmonic mean of these two quantities. So it goes, the important thing is that it goes from 0 to 1, and the highest is the best, is better. And the paper concludes saying, okay, if we tried at the time, GPT-4 was the best model, and they say, okay, actually, by looking at this data set with 400,000 examples, we see that the LLMs achieve close to random performance. So they are not able to infer a correct causation, like what caused what, from just looking at this kind of questions. But then our work was, I'm going to directly give the result of our work. So in our work, we basically, what we do, we provide structure to these kind of questions. And with this structure, given a baseline, so giving any model, we are able to improve the result of this F1 recall and precision. And in particular, for example, for a reasoning model already, Quen3, we are getting an F1 of 48, which is not great, but not too bad either. But the important part is the increasing of performance for every model. And how do we do that? So that we basically add structure, as I mentioned. This is not necessarily new. There is some papers, like for example, providing a scratchpad or providing a program edit language. So basically, you can provide the possibility to call Python. Or in this particular case, the only thing we did is the possibility to the model to generate a knowledge graph before answering the question. So the idea is, okay, you have the possibility, if you want, to generate a knowledge graph to guide you. And then once you have this knowledge graph, you can answer the question instead of directly answer the question. And that's how we managed to increase precision recall and F1. And this is the schema. So the schema is the baseline. In the bottom part, you just ask the query to the large reasoning model or large language model, and you will get a final answer, yes or no. In our case, we pass this to the large reasoning model, but he has the possibility to build a knowledge graph. We are going to use two different things. One is structure outputs, and the other one is structure generation, which I'm going to explain what's the difference. And then we pass this generated knowledge graph with the query to the same model, and we get a final answer. So it's a two-step, one-pass schema. Okay, so structure output. So basically, the way we do this is we want to provide a schema to the model so that he's able to generate a knowledge graph. So in this particular case, I'm using just Pydantic. But the idea is you want to provide him with some schema so that he knows what he needs to build. And this gets translated. Well, there are many ways to translate this, but this is one of them. You can translate them and give the model a JSON schema he needs to follow. And basically, that's the part for structured outputs. And this is basically what structured outputs does. But is that all we can do? Just prompt engineering? And the answer is no. We also combine this with structure generation, or constraint generation, some people call, which basically consists of, I'm going to start from a very basic example. If you want the model to generate a certain number of A's and then a B, this will be a deterministic finite automata to do that. And if you wanted to generate the same kind of thing, but this time with tokens, so the large language models, as you may know, they don't work with characters, they work with tokens or semi-words or sub-words. And the way you will, so if you take from the vocabulary of the language model, what are the accepted parts to stay in state 0 or to pass to state 1, these will be the ones that are accepted by the model. And once you have this translation with the tokens, then simply what you're going to do is for each state, you're going to mask the tokens which are not valid. So we are masking here the tokens, and we are renormalizing the probabilities in order for choosing always tokens which are valid. And the combination of these two two things, structure outputs and structure generation, is what allow us to know for sure that we are getting 100% correct knowledge graphs syntactically, and semantically it's being held by the structure output. So if you wanted to see from a simple regular expression to, for example, if we had a very simple sentiment analysis case, which just considers label positive or negative, this will be deterministic finite automata. But in reality, this in real life, but we do it automatically, of course, gets translated into this beautiful deterministic finite automata. And if you just look at the first part, which is label, the other two were positive and negative. You see that it's related to the tokens that are valid for each of these states. And basically at each of these states, you're going to mask all the ones that are not valid. So as a byproduct of this work, we are also able to generate knowledge graphs in general. So we also did it for some internal documents of Nokia. We also did it for Alice in Wonderland, and we also did it for some text related to Marie Curie, etc. So we have been having fun. But the important thing is, okay, so we are able to generate this for this data set, which is core to cause, and we are able to improve this result. But now what we are currently doing, so this is with Wentao, this is already finished work, and with new models, and basically making the model, instead of generating a general knowledge graph, to generate a causal through all the Markov equivalent classes. We are able to push these numbers to 87%, 85%. The important thing is that for each model, we are able to improve what the model will generate by itself. And this is the work with Han, which is there. And in this case, what we want to do is, so the core to cause model is a very simple data set in which the maximum quantity of variables that is available is 6. So with this, what we are doing here is to push it to 10, 20 nodes. And the idea is we first extract information, then we build the Markov equivalent classes, then we blanket through some method. Markov blanket is one of them, but there may be others. And then we basically remove irrelevant nodes from this big graph so that it stays within the context window of the language model, and it also just keep the important information. And yes, and then we reason with the LLM after we have obtained this pruned graph. So we already fill out this core to cause extension, and now we are testing. Are the results ready? No. And yeah, this is the current work. So in conclusion, so we used two different things. One is related to structured output, and the second one is about the structure generation, which help us to build that tool to the language model so that he's able to somehow use this to answer the question in a better way. This is inspired by a Scratchpad paper or by program-aided language model paper. And yeah, and simply providing structure to the thinking of the model significantly enhance the reasoning, the reliability, and the output quality of the answers of the agents. So just giving them the possibility to structure your thinking, which is what we humans are good at. That's it.
So I don't know if this is doable, but I'm just wondering what you think. So I've seen a couple of papers or talks lately where they're showing that LLMs sometimes know when they're being tested, when they're being benchmarked, right? Like they can tell that they're being tested. And have you seen these papers? So okay, anyway, like it's pretty amazing because like whatever, the recent one I showed, if they know 80% of the time they can figure it out. So when you benchmark an LLM and it does really well, all you've shown is that it's a good liar. So anyway, but I'm wondering if this idea of carefully checking for causation can be actually sort of applied in that context to help understand if, are we interpreting correctly when we, like, if the LLM knows it's being tested rather than revealing what it would normally really do, there's a causation.
Yeah.
I don't know if your work is applicable, but
Yeah,
that could be an interesting idea,
interesting.
maybe, I don't know.
Should, look into
Does that make any sense?
Yeah.
Okay.
A quick question, just maybe a point of clarification. You were testing whether the LM was good at inferring causality, right? Were all the examples that you were giving it combinations where the information that was provided was sufficient to provide, to make that answer? Or did you include instances where, nope, there's not enough information to include it no matter what? So that was it always, you know, I can tell whether it's yes or no, right? Or are there other cases where?
There are other cases. So in particular, I think that even this case, this simple example, sorry, but even for this example, so there are 3 possible scenarios, and basically in only one of them this holds. And the idea was that the model is able to tell, okay, not necessarily this holds. So it's okay. So that it's able to say no, this doesn't hold always.
Oh, so yeah, I was wondering if you tested your approach against traditional causal discovery algorithms.
Mm-hmm. No,
that's it. I mean, yeah. So we have
task,
causal discovery algorithms. That's
so the task is really related to translation in a certain way of natural language story into something that can be written as a normal causal discovery. So we are not, in a certain sense, testing, okay, does this algorithm perform better, or does the LLM perform better than the existing algorithm? It's really, in a certain way, a translation. And actually, one of the possibilities, and we don't have the result yet, but this is, okay, it's being tested and we have very good things, is that you could directly, if you knew that the question is about causality and you can use some established programs, and you are just translating and you are giving, okay, these are the variables, this is where you need to put them, and of course the result is very good because you are just using the engine. Here the idea was more related to the translation of natural language to a problem related to causation, and then within the language model applying this reasoning. So
okay.
It's slightly different.
Thank you.